Okay, hello everybody. My name is Juanito, and you're watching a video that I'm doing about how to turn your idea into a printed circuit board for pretty cheap using free tools on the internet that everybody has access to, and a website from China, a factory called JLC PCB. So my whole project has always been trying to help people create modular synthesizers using, even if they have no budget. Here's an 808 clap and maracas circuit that is built all on a piece of paper. All the components just kind of bundled on there like that. And since it's a 808 clap and a maracas, I have both. It never worked very well because it wasn't very loud. I could probably fix it so it worked better, but my interests lie a little more towards samples for snaps and claps and maracas type things. And I have some really good claps already in my modular, so I don't need this anymore. Plus, it's a whole pineapple lid as opposed to a smaller module. And here are two examples of circuit boards that I've had printed at JLC PCB. This is my double plus base. This was a double plus base. An earlier version, this one required only two fixes. That resistor right there and the volume potentiometer was wired backwards. This one works great. Look at it, surface mount technology. Okay, having said that, let's dive right into it. This is, I'm going to switch scenes so you don't have to see my head so big. There's my little head. And my browser's not popping up. Oh, I know what happened. Add new source. Browser source. No. Window source. There we go. Add source. Make it bigger. Perfect. Move my face on top of it. There we go. All right, I fixed that problem. We're going to begin with a tool for circuit design and circuit simulation called FALSTAD, F-A-L-S-T-A-D. I'll put links down below. When you click on the FALSTAD link, you will see this. You can delete it. And then we're going to be making a buffered mult. What that means, it's an active circuit which takes a signal from somewhere in your synthesizer and it turns it into three of those signals low impedance. The signal coming in doesn't matter what impedance it is. High impedance doesn't matter. The impedance that comes out will be low impedance. 1K is 1 kilo ohm is the standard impedance output level of Eurorack. And that's what we'll design. I'm going to move my face. Maybe that's a good spot for it right down there. Cool. So what we need for this is an input, 3 outputs, a quad op amp TL074 or 2 dual op amps, and the resistors, 2 LEDs. We're going to have it be 3 outputs. The 4th op amp is going to be driving LEDs. So with FALSTAD, I'm going to draw 4 operational amplifiers. 1, 2, 3, 4. That one's too long. Gotta match, right? We're going to put an in. Let's do power. The power is going to be plus 12. And minus 12. This cursor is gigantic. That's plus 12 again. It needs to be minus 12. So it kind of messes up my... Now Fallstat is going to complain if we do capacitors straight from the power, so we're just going to leave those power inputs right there, not touching the capacitors. But let's just assume they are. 10 microfarad is a really good value for generally all Eurorack modules. I like to put diodes for protection to keep for when you plug in your power header upside down the wrong way. So diodes right there. And then I'm going to use 2 dual op amps instead of 1 quad op amp. So we're going to need 2 100 nanofarad capacitors per chip. One for the positive rail and one for the negative rail. 100 nanofarads. When you're using 100, I'm going to hit Control C and then Control V. That gives me, look at that, it's asymmetrical. Got to make it symmetrical, don't we? There we go. And then I'm going to select both of those. Control copy, Control V. Right there. I'm only doing this because when we design the circuit in the software called Easy EDA, we're going to need to draw that on the schematic, because that way the program knows that those capacitors need to be included when you're making the PCB. I'm not going to draw the wires from here to the op amps. These op amps are already they're already powered. In fact, they're powered by positive and minus 15 volts. Look, see, 15 and negative 15. I'm not going to change it because it's not a big deal. So let's do I'm going to delete this. Now, let's have there be an input. Look, it says hello. We're going to change it to say input. That didn't work. Input wire. The inputs are going to go into the non-inverting input of these op amps. There we go. Input. Input. There we go. That represents input. Every op amp, the non-inverting input, gets its own input, gets its own wire going to it. We also need to include a ground reference resistor at the input. We can use just one. The TL07X series of op amps have unbelievably, ludicrously high input impedance. What that means is they are very sensitive to changes in voltage, even the changes in voltage in the air, just from lights, from static electricity, from weather patterns, anything like that will be picked up by the inputs of a TL07 4 or 2 operational amplifier, op amp. So with this, we need there to be an input, a ground reference resistor. That way the op amp will be like, what voltage should I be detecting on these pins? Should it be the 100 volts from the air that's coming from the wires in the wall? Is it the hundreds of volts from the fluorescent light fixtures? I don't know, but they're going to have problems. So we need to tell it, hey, you should be listening to ground. You should be copying the ground of your system, of the system. So we're going to use a 100K resistor from the inputs to ground. That way when nothing's plugged in, it'll be like, sure, I'll just do ground. I'll be grounded. It's nice to be grounded. These are going to be simple voltage follower buffers, which means the inverting input of the amp is tied directly to the output of each amp of the 3 amps that we're going to be using as the buffered mult output drivers. For the 4th op amp, we are going to use 2 LEDs that's L in Falstad, and we're going to put the 2 LEDs inside the feedback loop of the amplifier. What that does, see, LEDs only light up if you pass a certain amount of voltage through them. With a typical red LED, it's a, oops, not ground. I put a ground there, that's not going to work. Where's my cancel? There we go. We need to have there be a resistor. With 1K is fine. I'm going to rotate this because I didn't leave myself enough room. Rotate it the other way. There we go. LEDs require a certain amount of voltage to be passed across them before they'll light up. That can be about 1.5 volts in the case of a red LED. It can be 3 volts and even higher for ultraviolet, white, and blue, pink LEDs. Putting them in the feedback loop of an op amp means that the op amp is going to be putting out or sinking voltage, and it will be like putting out voltage, and the inverting input will be listening for that voltage. Do I see any voltage? The op amp will be like, no, and so it will put out more voltage, even at 0.1 of a volt. So when it ends up getting past the forward voltage of the LED, it will be like, aha, I'm detecting some voltage. So it'll be like, cool, stop putting out more voltage, because we have 0.1 volts going back in or being detected by the inverting input. So then it'll be lit very dimly. If you put a normal LED with 0.1 volts on the negative side and have ground on the other side, sure. Well, a resistor, current limiting resistor, the LED will not light up because that's not enough voltage to get past the forward voltage of the LED. All right, now we're going to put our output resistors from each output. 1, 2, 3. The standard output resistance, output impedance of a Eurorack module is 1K. Now, TL072 op amps and 4 have about 200 ohm between their output stages and the actual output pin. So technically we don't need to include these 1K resistors. They're just there because of the specification of Eurorack, and they're also there for peace of mind. They're kind of redundant. You don't need them to be put there. Most modern operational amplifiers are perfectly happy. Well, they'll get a little warm, they'll burn up some current, but they're generally happy being with their outputs directly connected to ground or the positive rail or the negative rail. They won't be damaged by that. It's very nice, especially the TL07X series and the NE5532. But don't use the NE5532 unless you know what you're doing, because they will pop if you try to use them in a weird way. I've popped so many NE5532s. We're going to make, plus they don't come in a quad package. In fact, the NE5534 is a single op amp, which is ludicrous. Okay, I'm going to put a voltage in. Run. Why isn't it running? Capacitor loop with no resistance. So maybe I'll just move the 10 ohm. Let's see if it'll play now. Run. Nope. Don't forget that that section over there, I'm pointing right at it.
It's 1 o'clock.
Don't forget that that power section exists. I'm going to delete it because it's messing. It's not wanting Falstad to run. So delete. But don't forget that it exists. We're going to need it later. There we go. Look at that. All the outputs are. Just a second. Vander arc. I had to do my work. Now, if you want to pass a control voltage through this buffered mult, it'll work fine. I'm going to make a test point. Put it right there, and it's going to read about 4 point. It reads exactly 5 volts. Well, these are ideal op amps, that's right. Give a new scope. Look at that, 5 volts. If we reduce this to 4 volts, guess what's going to happen on every output? It's going to drop down to 4 volts. If we change this from being DC to being, I don't know, a square wave, look at that. Plus and minus 5 volts. Change it to a triangle. Why am I doing this? This is completely... Alright, I'm doing this to show that the LEDs are lighting up gradually, even when there's tiny amounts of voltage passing across them. In fact, if we move the test point down to here, we'll see there be a jump where the I can't point. Sure, I can point with my pointer. See these areas right here? The voltage spikes because it has to get past the forward voltage. I'm gonna switch to a let's see, Schottky switching, general purpose germanium. There's no forward voltage setting on this. What? Come on, Falstad. All right, let's choose a Schottky diode for one of them. It's not going to light up, and it still lights up. But look down here, the vertical section when the negative in the negative half of the waveform is much shorter than the positive section. All right, cool. Now we're ready to start designing our my drive, my Facebook. There we go. Let's start designing the actual schematic using an actual software package designed for that purpose. This is Easy EDA Designer. This is the Easy stands for easy, and EDA stands for electronic design application. That's my random guess. So this is the schematic creating and okay, what am I doing? Oh yeah, I'm going to click on Easy EDA Designer. This is how we're going to design the schematic that we're going to use to create our buffered mult PCB. We'll design the PCB in the this same software. You can see that I already made a buffered mult. I made it last night, but the sound quality was bad because I didn't have a lavalier mic. But today I do have a little mic right there. So hopefully the sound quality will be better. We're going to make a new project. A new project, let's call it buffered with no space. Buffered mult. Save. And we're going to see a beautiful blank empty schematic. There we go. Let's begin with the power. With Easy EDA, you have all the components you could possibly imagine wanting in this library thing that I'm looking at right now. I've already developed my own personal library, my libraries, my favorites. When you start out, you're going to have to be developing your own library, and that might be a pretty annoying thing to do because we'll cover all of that soon. You need to use basic parts. You need to use parts that are in stock. You need to use parts that have good footprints and schematic symbols. But right now, I'm going to search for a power connector, which is going to be under my favorites for IDC connector. Everybody knows what IDC stands for. If you know, you should drop it in the chat because I totally know what it means. But just make sure you know. Where's my boundaries for my schematic? Why is there no... Oh, there we go. I accidentally clicked... Okay, so I was editing the footprint. That's a useless thing to do. All right, so for my buffered mult, here is the schematic. Spacebar rotates. Middle mouse button or right mouse button drags the canvas. I'm going to put it upside down. There it is. The next thing I need is wire. Mr. Dopfer, and I assume it was a dude, his infinite wisdom, decided to make the power connector standard for Eurorack have pin number 1 be the negative power rail. If you know anything about, if you've ever owned a Eurorack module and looked at it and plugged it in, you've been looking at the connector and you thought to yourself, why does the red stripe go toward negative? Red in generally electronics means positive voltage, current, but in this case the red stripe indicates pin number 1. So 1 and 2 are negative pins. 357, 864, those are ground pins, and 9 and 10 are positive pins. The first thing I'm going to put is a capacitor to ground as a power conditioning capacitor, multi-layer ceramic capacitors. You can see those on this right. You can't see that. Let's choose a 10 microfarad capacitor. We're going to do one here, and we're going to do one here. We're going to stretch this ground out, and then I'm going to move the capacitors so the one side of the capacitor is touching the ground wire connection lead trace ground pore, and the other is connected to the power coming off of the positive and negative pins of the IDC connector, International Department of Connectors. Pretty sure that's what it stands for. In my library, I've already got some Schottky barrier diodes. The positive side is going to be going that way. The negative side is going to be going that way. Yeah, I'm pointing that way. Cool. Now, easy EDA and probably all electronic design softwares will put the entire long designation of components like this. I don't really care. I know which one I chose. The Schottky diode, which has a lower forward voltage. All diodes have forward voltage. Germanium and Schottky have the lowest. Schottky is really good because it lets plenty of current through. Plenty for this circuit, at least. All right. So I like to delete the long component designation. In fact, I like to move my component designations closer to the actual components. That way, this, as hideous as this schematic is going to end up being, it's a little bit less hideous, a little bit less disgusting. Personally, I appreciate beauty in my designs, So the schematics that I draw, I take a lot of care to make them look pretty and cute and silly and funny. But it's really hard to do that with electronic design software. I don't think EasyEDA is unique in that. All the machine-drawn schematics that I've seen, none of them are really beautiful. All right, now I've chosen a 100 nanofarad capacitor out of my favorites. By the way, the reason these are my favorites is because if you look down there, it says 0603. That's up there. I forget. I'm not up at the top anymore. And down here it says they're 0.2 cents each. That's a good deal. There's, what's that, 24,394,000 in stock. That's plenty. Minimum 50, which means we're going to end up paying whatever 50 times 0.2 is, I think 10 cents. So we're going to end up paying 10 cents for these no matter how many we use. All right, I'm going to place this 100 nanofarad capacitor right here and right here. And then I'm going to put two of each, the above and below the ground rail, because each integrated circuit, each chip needs its own pair of decoupling capacitors. Up here it says VCC. That's the more positive voltage rail. And then we're going to choose VEE, which is the more negative voltage rail. Cool! Look at that. We have the power section done. Now we can start placing chips. We need to look at our library. And over here we have FET input amplifiers. FET stands for Field Effect Transistor. Whew, I remembered. And I have two in my favorites list. Let's check it out. This one's 31 cents and it's a quad op amp. Down here it does not say that it's basic. Nope. Okay, so there's two kinds of components. Well, there's three. One component is a component that JLC, PCB, or LCSC doesn't have access to. Certain potentiometers, certain LEDs, things that they would have to solder into the board by hand, like the power connector or your potentiometers, which, oops, I pointed the wrong side. Power connector, potentiometers, whatever. You don't want to pay some tech to assemble those, at least. I don't think you do. Maybe you do. Go ahead. That's cool. But I like doing it myself. The TL074 is not a chip that they have in stock basic, which means if you include non-basic chips, they're called extended. If you include extended parts in your build, you can end up paying a per extended part fee. It's like $3. If you're cool with spending $3, whew, money bags, McMoney bags. Go ahead with your bad self. This dual op amp is a basic part, which means you're spending 27 cents as opposed to, well, times two. So about 54 cents compared to 31 cents plus $3. If you're going to be building 1,000 of these, go ahead and use an extended part. That means some technician in China at the machine, at the factory, will have to take the reel, take the reel out of a box, stick the reel of chips in the machine, thread it into the machine the right way to the pick and place machine. Oh, it's so cool. I would probably hate working in that factory, but I would sure like to see a video about it. Now we're placing our two operational amplifiers. I'm going to delete that because it's ugly. Move U1 down there. Going to delete this because it's ugly. Move U2s down there. U2. With or without you. Now we need to have inputs and output jacks. In my library, I have already found a FunkyCon mono jack with a footprint that I like and a schematic symbol which I find non-objectionable. Here it is, ThonkeyCon 1. You're going to have to look for one yourself. I don't know. There is one of them. We're going to have one input and 3 outputs. Spacebar rotates. Cool. Now we need light emitting diodes. I have a through-hole LED schematic symbol and PCB footprint. I like using through-hole LEDs because, for things that you want to see, because that way you can have them extending through the panel and you can look at them with your eyeballs. You don't have to be looking at the... Oh, I clicked on edit part. Library place. Let's use this one right down here as the one for the 2 LEDs. Look at that footprint. Those arrows are completely different from each other. Not footprint, schematic symbol. It's just ugly. I disapprove. Whoever made that footprint or schematic symbol should just find something else to do with their life. D3, D4. Cool. Now let's start dealing with the jacks. First, what we need to do is deal with the pins that are grounded or not used. The sleeve of a ThonkeyCon jack is connected to ground. I know I'm blowing your minds right now, but that's the way it is. Ground, ground, ground. The normal pin which makes contact with the tip when nothing's plugged in isn't going to get used in this build. This software will complain if you try to create a PCB without telling the software which pins do not get used. It's great because then when you miss a connection, it's like it flags it and says, hey, listen, bro, you forgot to tie this pin to something. So this little X right here is exactly what you need to put on each pin or connection that is not going to get used. Now let's do a resistor. Let's do all the resistors right now. Let's choose a 100K resistor for the ground reference resistor, which is going to go... I hit C. I don't know what C does. Oh, it makes a circle. We don't need to be making circles, so let's not do that. Undo, undo, escape, undo. Escape, got rid of it right away. All right, we're going to place a 100 kilo ohm resistor to ground. Now, if I was making this schematic for something that I cared about, I would be deleting everything, all the ground, where it says GND in that really unpleasant font. That typeface, look at it. The kerning, the G should be much closer to the N. Why are there 4 stripes for the ground? Should be 3. Anyway, I'm wasting time. All right, 100K resistor to ground, so the inputs of each amp don't flip out, or so the amps don't flip out. I'm going to use this dooley bopper, which is called a net port or a net flag. That's going to be my input. What this does is it enables you to put connections all over the place without having there be wires, traces, leads, lines, schematic things messing up your design. Very useful. This is exactly as though you had drawn wires from each, oops, what is that? It's a rectangle. I think I hit R instead of W. You know, drawing lines everywhere, right? You don't want to do that. Or maybe you do. Go ahead. Go on with your bad self. I said I was going to do all the resistors, and then I just did one. So let's do all the resistors for real. These are the output resistors. They are placed in series with the output, which basically means that the current needs to go through those to get to the output. The current doesn't need to go through any resistors, any components besides traces to get to the inputs. Ah, you know what I forgot to do? I forgot to include the voltage connections. This VEE is basically a special customized net port flag. Is that what it's called? Net port? Yeah, net port, net flag, which is for the negative power rail. Going to connect that to the negative power rail of that op amp and of this op amp. And then we're going to change that to the positive VCC and click on it again. And there we go. I can never remember between VCC, VSS, VEE. SS is source, CC is collector. I'm not as good at electronic theory as I wish I was, but I should probably be better. Now, you'll remember from the Falstad simulation, Shift, Tab, Shift, Control, Tab. There we go. From the Falstad, that, what was I even going to say? Oh yeah, the way the op amp is wired, the inverting output is connected directly to the, I said inverting output, I meant inverting input, is connected directly to the output. So what we need to do is put a wire between each output and each input. Look what I did, I made a little extra bit of, cool. We have one more to do that with. It's right down here. Oh, you know what I didn't do? I did not put the current limiting resistor on the, I'm going to select one of the resistors I already placed, hit Control C for copy, and Control V for paste. And I'm going to put it right there because let's go ahead and say that is where the inverting input of the op amp is going to connect to. Now let's draw some wire. Well, first let's put a ground on the other side of the current limiting op amp, current limiting resistor, and then let's draw our wires for this part. Okay, this side is going to go to the output, and this side is going to go to the inverting input. There we go. Cool. That part will work. Let's use net flags. This is fun. I like doing this. Look what I'm going to do. I'm going to say output 1. And then I'm going to choose the net flag again. It says output 2. It's so much fun. Good enough. And then do it again. What's it going to say? Output 3. Then it says output 4. We don't need output 4. I'm going to select it again. I'm going to put it by the top one. We'll change the name of it to output 1. And then we're going to click it again, and guess what it's going to say? Output 2. It's so smart. It's fun when you get to do less work. I would even say it's a delight. And I believe we are finished with creating the schematic. Let's see, we have 2 chips with 2 op amps per chip, so we have 4 op amp stages, 4 op amp doodly boppers, gates. We have 1, 2, 3, 4, 5 resistors, 6 capacitors, and 2 Schottky diodes, and 1 IDC connector, I don't care, that's what it stands for, and 2 LEDs. LED stands for light emitting doohickey, with the worst arrows I've ever seen. Why are they don't even match. I don't care. IDC. I'm going to click the save button because this really cool thing design. Look at that. Under the hand it says convert schematic to PCB. Let's try to do that now. It's not going to work. It's going to say save your project first. Down here in the lower, oh, my face is in the way. Down here in the lower right will be error messages. Sometimes you'll click stuff and it won't do anything. It won't respond. You'll be like, why isn't it responding? Then you have to look down there and it says some random nonsense. Now, not saving your project, that's not really random nonsense. So let's go ahead and save the project. Did you see it said save successfully right there? I'll do it again. Oh, it's grayed out. Okay, never mind. So now we can go to convert schematic to PCB. PCB stands for printed circuit board. I know so much stuff. When it pops up, it's going to say new PCB. Sure. Units, millimeters, that's what I prefer. Maybe you like mils if you're in the United States or Austria. Maybe they use mils all over the world because we invented printed circuit boards in the United States. And then board outline rectangular. We don't really care about that because we're going to change the board outline anyway. The first thing I do is delete the board outline. You know what? I'm going to actually make a board outline. I'm going to do tools, set board outline. I'm going to choose the width to be 25 millimeters. The height, I'm going to have it be 100 millimeters. Start 0. Why is it mils? It should be... Why is it mils? Cancel. Edit. Sorry, I might have to fast forward past this part because this is probably really going to end up being really boring. Aha, maybe it's over here. Units mil. Nope, millimeter. Yes. That was nice and short. We probably don't need to edit that out. So, tools, set board outline. Width 20, 5, height 100. And now I have I'm going to do it again because I forgot to say I want it to be start X 0, start Y 0. And now it's under. Why did it go negative? What's wrong with you weird software? I guess I'll just click on it and try to drag it. Nope, it's not working. Alright, I'll click on it and then push the up key. Maybe shift up key. Nope, no faster. Control up key, alt up key. Alright, just up key. That hold music that has a bunch of fans. Oh, we're done. All right. First, let's put the potentiometer. No, there's no potentiometers. First, let's put the input jack. Which jack is the input? IDK, which stands for I don't know, but I do care, which is what IDC stands for. So let's try to figure it out. We'll go to the schematic up there, and we will click on the part. We could look at the designation, that's U3. We could go and look at each one and see which one says U3, or we could hit Shift X. which it failed to do. Probably because I failed to save the PCB. Saved successfully, it said on that piece of toast that popped up under my face. Shift X. It was that one. I got lucky. All right, we're going to move that up to the top. Cool. And then with circuit design, where you place the components, kind of a big deal. You want to minimize the length of your traces, and you want to minimize how often they cross over each other. Routing circuit boards is an art form. It is something that is very rewarding, and it's something that can be quite challenging, quite difficult. I will leave it up to you to decide how you want to route. I'm going to do something called an autorouter because that will be easier, and I don't feel like hand routing everything. However, there's people who love hand routing. Cool. I respect those people. Go ahead and do that. So anyway, now what we need to do is decide which, let's go back to the schematic. Look at the outputs. It's 4, 5, and 6. So let's go and do 4, 5, and 6 because output 1 corresponds to the top of U1. Output 2 corresponds to the other side of U1. So having 1 and 2 be right next to each other. You know what? I'm going to not do it that way because the LEDs are on U2. With or without you. With or without you, my love. So anyway, U2 is going to go above U1, which means the LEDs and U6, which is the last on the schematic, the most bottom one, will go above it. My two LEDs are going to go right there and right there. What are we going to do with the IDC? Yeah, I don't care. I don't know. Let's put it over here. Let's put it a little higher up. Let's put it right there. It won't fit crosswise, so when we need to hit spacebar, rotate it that way. All right. Ooh, I'm going to do something. Look what I'm going to do. This is a fun trick. I love this trick. I'm going to go up to Tools, and I'm going to click on Net Color. Nets. Ground. I'm going to tell ground to be a gray color. That one. I'm going to choose BCC. That's the more positive one. I'm going to choose a fun pink color. Where's a cool pink? There's a cool pink. It's probably magenta. Now let's do VEE. VSS. Psh, what's wrong with me? That one's going to be green. In my synthesizer, all the negative voltage power rails are green. My positive power rails are orange, but orange is too close to the red and the yellow colors that are already being used by JLC, PCB, Easy EDA. Okay, cool setting. So when we do that, look, where the positive and negative power rails connect are in those colors. Where the ground connects is going to be a gray color. So cool. Can't even stand it. It's great. Okay, let's place the capacitors. You know what? I'm going to drag all of these parts up here where, you know what, let's just drop them all willy-nilly on top of the parts. I'm going to put C1, which looks like it is you know what? I'm going to have to cross probe C1. Okay, C1 is on the positive side of things. So where's the positive going diode? I hit Shift X, which means cross probe. Goes right there. I turned it around. look at these component designators. They're all... Okay, so when I'm building a complicated PCB, one of the last things I like to do, that makes it sound like I don't like to do it, one of the last things I do is go through and change the height of every single designator. I click on it, I go over to the right there and say height 0.6. And that makes it smaller, and that way, that's my little visual confirmation. I put this part where it needs to go, I'm happy with its placement. I don't need to move it. The tracing, everything is good, the routing. C2 goes down here as well. These blue lines are called rat lines. And the rat lines even change color depending on what net they're connected to. This rat line is green because it's connected to VEE. Pretty cool. Thanks for being such a cool piece of software that we can use for free, Mr. Easy EDA. Alright, cool. Now, since the positive rails are at the top of this I don't care connector, and the negatives are down there, let's go ahead and do the chips the same way. I'm turning it around to the point where the pink is up top and the green is down below. Oh, if you're watching this, well, you're probably saying to yourself, what the heck, Juanito? You're drawing, oh, also remember U2 goes below U1. With or without you. What was I saying? Oh yeah, these FunkyCon connectors. In fact, you know what? I'm going to do a fun little trick. I'm going to pull all the components inside the board outline. This isn't where they're going to go. And then I'm going to click a little thing right here that says 3D. And we're going to see a problem with what I'm building so far. Oh no! The power connector and the FunkyCons, the audio connectors, are on the same side of the board. What the heck? That's not going to work. In fact, look, they overlap each other. Amateurs. So what we have to do is move the audio connectors and the LEDs to the other side of the PCB. We do that by using the Control key and the click key on your mouse, selecting them all, and now they're all selected. These are all the parts that need to go on the other side of the PCB. Over here, it says add them to BOM. Actually, no, we do not want to add those into the BOM. BOM stands for Bill of Materials. I was going to make a scatological joke, but I decided not to. And we're going to move them to the bottom layer. Another opportunity for a scatological joke, which I'm not going to take. All right. I'm going to highlight the the FunkyCon connectors. Oops, I used Shift instead of Control. Oh, and also look now, we can tell they're on the other side of the board because they say U4 backwards instead of U4 the front way. Euphoria. Did anybody watch that show? I do not watch that show. It has Zendaya in it. Now, we have all those four FunkyCon audio connectors highlighted. We can use one of these tools up here, these little clicker dealy boppers, to make them be aligned with each other. They're all the same width, so we don't have to worry about left or right. We can just do center. If they were different widths from each other, like if you had potentiometers and jacks that you wanted to get lined up, you'd want to use this down the center one as opposed to the left or right one. Now, I'm going to take these bottom three, Control click, Control click, Control click, and I'm going to make them equidistant from each other by clicking that thingy. Now they're all in a line. The bottom three are equidistant from each other, and I think we are happy with the placement of the let's go ahead and click 3D to make sure we like the way that looks. Oh no, where'd they go? Remember, we moved them to the other side. There they are. Cool. The LEDs are in a stupid place, but the connectors look great. We'll probably put the LEDs basically right there, but lined up with each other, and centered with the, yeah. I'm also thinking this is a little bit too wide. We could get away with making this a 2 HP module. Most buffered mults are 2 HP, but I'm going to leave that up to you. You can figure out how to make this narrower. We're just going to design this and pretend to order it because that's the point of this video. All right, let's move the LEDs out of the way and figure out where we should put the op amps. I'm going to put one of them right there. I'm going to put the other one right there. Vander Arc. My job is so hard. Cool. Now let's place the capacitors. These are the capacitors over here on the, yeah, right there, exactly right there. They're not in the schematic, they're not actually placed by the pins, but we do need them to be placed as close to the pins as convenient. Since the Funky Kong audio connector is on the back side of the board, it's okay for our footprints to overlap. That's fine. The thing you do not want to overlap is where things go through the circuit board. That's not okay because the IDC connector pins would be interfering with the plastic of the Funky Kong jack. Moving it farther over, well, the plastic of the I don't care connector will be interfering with the pins. So we need to, that's fine, for instance. It might get a little tight if you need to solder things. You might have to pay attention to the way you put it together, the way you assemble it, to make sure you're not giving yourself no room to work with. All right, we're placing the decoupling capacitors. Some people I respect a lot never use decoupling capacitors. TBH, you could get away without using them because we're probably not going to be doing mission critical radio frequency type stuff with our silly DIY modular synthesizers. But it's good practice. I built a bunch of power amps, gain clone power amps, using the LM3886 chip, which is a 100 watt, depending on voltage and load chip that is like an op amp, but it can handle outrageous amounts of current draw. And I didn't include decoupling capacitors because I was like, what? I have like giant bulk capacitors. I have like 50,000 microfarads of capacitor right there in the power supply. What the heck do I need little 10 microfarad capacitors on each chip? That's stupid. And so I very carefully, this is the input resistor of this, output resistor for this particular output. Back to my story. I built the amps point to point because that's what you do. And which one is this? Oh, this is the input one. Okay, this needs to go up here. Now you could cross probe all of these with your Shift X. Let's do that. Shift X. Oh yeah, the input resistor, 100K, cool. Shift X, back, but pow. So I very carefully built all of these power amplifiers. I just moved R3, like the designator R3, not actual R3. R3 goes down there. So I built them all very carefully, made sure they were wired correctly, drilled the holes in my big ol' heatsink to keep them from melting or going into protection, and turned it on, and shrapnel started flying around my basement. I was like, what the heck? Turn everything off. Look at all my chips. I think I had 4 on the board. And they had popped. Pieces of the package had chipped off and flown past my face. They didn't hit my eye, luckily. And so I was wondering what in the world happened. So I built another one and very, very carefully plugged it in, and it was working fine. And then I touched like its input with my finger, and it popped. So let that be a lesson to you. It was definitely a lesson for me. Make sure you put decoupling capacitors on every chip. I'm kind of moving parts around in a way that seems to make sense. Now let's move the LEDs. Why is C1 designated way up there? Let's make sure they're both even with each other. I didn't hit Control click to select. Cool, they're even with each other. Now let's try to make sure they're even with the... Okay, cool. This is what we'll do. I'm going to turn this one around. I'm going to lock this ThonkeyCon. Lock is, I think, right under my face. No, it's right there. It says locked, no. We want to say locked, yes. So now that ThonkeyCon is locked. Can't move it, can't move it. I'm going to select this and the ThonkeyCon. And then I'm going to say, let's make them line up this way. Come on, work. All right, cool. When one of the parts you're trying to line up is locked, that means it's going to move like Zeno's arrow. It's going to get closer and closer and closer. Luckily, with the snapping, it will actually arrive where it needs to arrive, not like Zeno's arrow, which never will arrive. So then I'm going to use the arrow key and push it to the right, let's say 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do 15 times. 11, 12, 13, 14, 15. That looks good. Now we're going to do the same thing. Click the ThonkeyCon. Control click the LED. Do let's line up to the right. Nope. Let's line up to the left. Okay. Line up to the left. I mean, left. And then I'm just selecting the LED and I'm pushing to the left 15 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Done. I do not have a 3D model of the LED in my Easy EDA favorites. So when I click 3D, we won't be able to see the LEDs, but we will see everything else. Pardon me, I hiccuped. And that looks great. Again, it's too wide. Placing the IDC across the board right there might make more sense. Some IDCs that you'll be able to find in the, like power headers that you can find in the library, are surface mount. If you have the surface mount parts, that's a great way to go, because then you can place them wherever you need to, as long as they don't interfere with the through-hole pins from the other side. And you can make this be a narrower project. Now that we're done with the component placement, I'm going to click Save by clicking the very strangely shaped icon, which if you're my age, you remember floppy disks. But if you're 20 years younger than me, you probably never saw them in real life. I forgot something. We're going to create a ground pour. What we have to do is get this out of the way. Click that. It says copper area, E. What net is it going to be connected to? Ground. With the copper area, what you do is you click. I'm going to click outside the borders of the PCB. Click. Use your right mouse button to drag, because if you use the middle mouse button to drag, which also works for dragging, it also places extra nodes on this copper area. And then when you're finished with the area, right click means poof, finish the copper area. And then it will build the copper area. Cool. But what's this? You have these really thick spokes connecting the ground to the copper area. From experience, those spokes, this one is made with spokes that wide, that's too wide. You want them to be narrower. So we're going to select that copper pour by selecting the dotted line that is around it and specify how wide you want the pad connection spokes to be. I choose 0.4 because 4 is my favorite number. It really is, even though it means death in Korean and Japanese and probably Chinese. Yeah, definitely Chinese. We watched Turning Red, which is what this PCB did, and they talk a lot about that. Now we're going to make the PCB turn blue. Okay, I have toggle view installed, which is that right up there. Which means when you click bottom layer, it flips the view. That's a plugin you can install in your own copy of EasyEDA if you so desire. I'm going to make another another copper area. I'm going to duplicate the work I did on the front side. Click, right mouse drag, right mouse drag again. That was a failure. Select that copper area and delete it. Do it again. Copper area. Ground? Yes. Click. Right mouse drag. Don't go as far this time. Click. Right mouse drag. Zoom out to make it easier. Click. Right mouse drag and left click. Right click to create the copper area. Select the copper area. Change the spoke width to 4 point def. And again, of course, this is millimeters, not mils. Now we have wonderful copper pour all over our board, but none of the parts are connected to each other because we haven't done any routing yet. I'm going to, this is stupid, you shouldn't have your LEDs like this. I shouldn't have my LEDs like this. So I'm going to rotate them like that, so that plus corresponds with minus, and plus corresponds to minus. And look, it left holes in the copper area. But that's fine, because the copper area, you can rebuild it either by clicking on an area where there's just the copper pour, copper area, rebuild all, and it'll fix those two holes. Yeah, see? But we want there to be routes all over the place, don't we? We are going to do auto routing, and we're going to use the cloud. The cloud, you guys. Run. single click, it's going to auto router is running. It's not running very well. Should be much faster than this. It's probably going to fail. Bing. Ding. Ding. If we stop it and try it again, it's going to fail because it'll be like, hey, stop trying to do two at the same time, loser. Alright, I'm going to cancel. I'm going to click save because I don't think I saved it. Connecting to server, maybe. Oh, it is connected to the server. Route, auto, route. Do the limitations. See? Do limitations of router server resources, multiple routers executing concurrently are not supported. Please try again later or do it manually. Yeah, do it manually, loser. A lot of people really prefer routing by hand. All right, we're going to try it one more time. Run. Checking local auto router server. Run. Auto router is running. I don't think it's going to work. There must be a problem with... Notice, easy EDA will be down temporary maintenance at 4:10. It's not 4:10, is it? No, it's 4:06. Yeah, it's April 6th. Okay. I'm going to Alt-Tab to my desktop. And I'm going to... Where's my desktop? Control F. Escape. F11. Oh no, now you're going to see my... all my shortcuts and all my other windows that I have open, which is going to be so embarrassing. What I'm going to do now, F11, is, I think I'll just go to black, right? Oh no, it's just staying there. Okay, cool. I'm going to start, you can't see what's going on, but I'm starting my own local auto router. That is a program you can download. It'll run on Windows, Linux, or Mac, and it creates a local server just in a terminal window. I'm using Windows, so it says win64.bat, which is the, I guess, terminal program command prompt. Okay, so let's go back to the browser and try doing the auto router again, and this time we will do local. It says available because my little batch file is running down there. Oh, let's hide that because I don't want you to see all the... I don't want to say what I was going to say. Okay, run. And it'll be like... Oh, no, oh, it is running. Okay, good. Now it's like saying, where should I put all these wires? It's going to be like, yeah, let's put them right there. Oh, I found a better way. Easy EDA's auto router is not very good. 10 vias, that's pretty bad. There is a router called a free router, which does a way better job than Easy EDA's auto router. With a simple PCB like this, not a big deal. With a complicated PCB like this, it's a bigger deal. You probably want to use free router. Did I say free router before? I think I said auto router. Free router, you want to use that instead. It's free. It's a little bit weird. It's not very good looking, but it functions great. It's fiddly. You have to export a export auto router file DSN, which stands for don't say my name. And then when you're finished, you have to import. Anyway, when you're finished with the auto route and it works, then what I like to do is hit Shift M, which hides the copper areas. And then I like to go through and make the traces wider so that they are lower impedance. The way you do that is you click, you hit W for wire, And then you click and look, now you're pulling a new trace. But then I hiccuped again. I changed the routing width to, say, since this is power, come on, get out of there. All right, so I'm going to shut that too. Now we have a teeny bit more area. Change my routing width to 0.8. And then look, it's a nice chunky boy. Right there. Wow, look at how big that is. And then you go to the underside of the PCB, which is probably going to flip it. Sure did. And then wire. If you click, oh, it worked. Cool. You can move stuff around like, okay, you can delete stuff. If your traces are going to interfere with other things, you'll see that X. That means, hey, it's touching something else. In this case, it's just touching the ground, the copper area. NBD, that means not a big deal, or no big deal. Let's keep making that trace wider. If you start your trace on an existing trace, the resulting trace that you draw will be the same width. So that's a fun little thing if you want to do that. If you can't fit traces, like, oh no, I can't fit it between that pad right there and that trace right next to it, you can always like move traces out of the way. But you can't put them outside the PCB, because how would the electrons flow? And you can't put them, you have to watch out where you put them, because maybe you'll accidentally move it to somewhere else where it's going to not work. I'm not going to do a ton of this. I'm just going to do a couple more. Oh, see, I moved that one way out of the way. And that's going to be a problem for me, probably. Try moving it back, see if I have room. Psh, barely. Wow, okay. Okay, so then you will want to go over your whole board and basically do this. Make the connections larger, wider, faster, stronger. A pig in a cage on antibiotics. Radiohead. If you think that two things need to be connected, you might be mistaken. Like if you're like, oh, the power pins are right there, up in the, it says PL underline 1, and that's power. So obviously the power needs to be connected there. So you're like, why come it not work? Why come no connection? Well, that's because the software knows that's actually, it's connected through that diode, that Schottky diode right there. So anyway, there we go. We are happy with this. Oh, whoops, I forgot to rebuild the copper. I'm going to click on an area with no components, right click, copper area, rebuild all. It'll rebuild, and then we have to hit Shift M, so we're looking at it again. It's so pretty. Satisfaction. Push me, and then just touch me till I can get my satisfaction. Okay. Push me, and then just touch me. Now I'm going to save it. And then I've already logged in to JLC PCB. See where it says sign in? You know what? I must not be logged in. So I'm going to sign in. Don't look at my login information. I'm going to sign in via Google. Don't look. Secret thing that I clicked on. Don't look. All right. So now you have to be logged into JLC PCB. Yeah, JLC PCB. You have to be logged in, or else this next step won't work. I Alt-tabbed before it, Control-tabbed before it went back to that. So you didn't get to see what popped up. So what we're going to do is click on Fabrication, one-click order PCB / SMT. SMT stands for Surface Mount Technology, which refers to the entire sort of infrastructure of building circuit boards using surface mount devices, which is what SMD stands for. It says order data generated finished. That's not generated finished. Please click OK button and continue. Maybe a native speaker did not write that sentence. I recognize, as a native speaker, my incalculable privilege processing Gerber files. And far be it from me to mock someone who learned Chinese and then had to learn English well enough to write these things. That's bonkers. Amazing. Okay, so here we have a picture of the PCB we want. That looks great. You can make it out of FR4, which is like that fiber reinforced plastic, or aluminum, which is cool. I've never done that, but it's probably pretty cool. I'm going to do FR4 though, just for imaginary, aluminum. If you click aluminum, it only does one layer. Okay, so aluminum is probably only good for like LED. Maybe it's because you can't do a via with aluminum. How would you even do a via with aluminum? You'd have to have it be coated with some solder resist and then plated. Crazy. Anyway, dimensions 100 by 25, that looks good. We're going to order 5 PCBs. That looks good. Single PCB, yep. PCB thickness 1.6, that looks good. Green, purple. Purple does not work with SMT. I know white does, and I know red does, and I know black. I don't know black does, but I think it... I don't remember if black works or not, but red and white definitely do. Because this is red, and this is white, and this is where I ordered these from. Lead-free HASL. Yeah, I want to click that because I just am. It's more responsible. Okay, cool. SMT assembly. Click. And then it thinks, and then you click next. Look at that price right there. $12.70. So then it's going to go to my cart. I got a bunch of stuff in my cart. It's going to say like $80, I think. But if this was all we were going to order, that would be our price. Waiting, waiting, waiting. Cool. Next. The assembly BOM, bill of materials, and the CPL. I don't know what CPL stands for. Got uploaded properly? CPL. Component placement library. I click next. Oh, shut that down. Oh, correct usage description. I've never had to do that before. Electronics and hobby DIY. Cool. What? I mean, I'm not building a guided missile or anything like that. Okay, we have to look and make sure we're not ordering stuff that... Okay, here we go. This P1 is the IDC power connector. We want to take that off unless you want to include it and pay a technician in the factory to solder that onto your board. I already removed the ThonkeyCon jacks from the BOM, and I also removed the LEDs are not in the library. There's no option for those to show up. So next. $16.82. I guess we had to pay for surface mount technology. The IDC is not in the order. Save to cart. Now if I order this, if you were to click order, this would show up on your doorstep in like a month. Oh yeah, there's my faceplate. Cool. $16.82. That is $16.82 for 5 buffered mults with all the components besides the jacks and the power connector and the LEDs already put on. That shipping might end up being about $12, maybe $15. I'm sure it's more if you live in other countries, maybe less if you live near China or in China. And that is that. I hope you enjoyed this video. Make sure to like and subscribe and watch to the end.